Beyond functions, serverless design patterns for modern cloud applications. Chapter 1, The Serverless Revolution, Understanding the Paradigm Shift. The world of technology is in a constant state of evolution, always seeking new ways to build, deploy, and operate applications more efficiently and reliably. In this journey, we've witnessed significant shifts in how we manage the underlying machinery that powers our digital world. Understanding this progression is key to appreciating the profound impact of serverless computing. The journey to serverless, a brief history. Our story begins not so long ago, in an era dominated by physical machines. From bare metal to virtualization, in the early days of computing, applications ran directly on specific hardware, known as bare metal servers. This approach was straightforward but inflexible. If you needed more capacity, you bought another server. If one server failed, your application went down. Managing these individual pieces of hardware was a continuous, resource-intensive task, involving everything from cabling and power to operating system installation and patching. The first major leap forward came with virtualization. Technologies like virtual machines allowed multiple independent operating systems and applications to share the resources of a single physical server. This was a game changer, improving resource utilization, simplifying hardware management, and enabling faster provisioning of new application environments. You could now create a new server instance, albeit a virtual one, with a few clicks rather than days of procurement and setup. The rise of containers. While virtualization abstracted the hardware, containers took the abstraction a step higher. Technologies like Docker and orchestration platforms, such as Kubernetes, allowed developers to package their applications and all their dependencies into lightweight, portable, and self-contained units. This meant an application would run consistently across different environments, from a developer's laptop to a testing server to production. Containers streamlined deployment and introduced concepts like microservices, allowing larger applications to be broken down into smaller, independently deployable pieces. However, despite their power, containers still required you to think about servers. You still had to provision, manage, and scale the underlying hosts where these containers would run. The leap to serverless. And then came what felt like a truly revolutionary concept: serverless computing. The name itself is a little deceptive because servers are, of course, still involved. They're just not your servers to manage. Imagine a busy restaurant. In the bare metal days, you'd own the whole building, hire all the staff, manage the kitchen, and pay for everything whether you had customers or not. With virtualization and containers, you might still own the building, but you're now more efficient, using shared equipment and modular kitchen stations. But with serverless, you move to something more akin to a modern food truck park or a cloud kitchen. You provide your recipe, an order comes in, and a fully managed kitchen service prepares just that one dish, charging you only for the ingredients and the cooking time. You don't worry about the ovens, the electricity, or the staff shifts. This dramatically simplifies the entire operation. The concept truly began to solidify around 2014 with the introduction of services like AWS Lambda. Suddenly, developers could upload their code and have it run in response to events, without ever specifying a server type, operating system, or even managing a runtime environment. It was a liberation from the burden of infrastructure management, redirecting focus squarely onto the application logic itself. What serverless really means, more than just functions. The term serverless is often narrowly associated with functions as a service, or FaaS, like AWS Lambda, Azure Functions, or Google Cloud Functions. While these ephemeral functions are indeed central to serverless, they are only one piece of a much larger puzzle. Serverless is not just a technology, it's an operational model and an architectural pattern. Let's explore its core distinguishing tenets. No server management. This is the headline feature. You completely offload the responsibility of provisioning, patching, updating, or maintaining servers to your cloud provider. No more operating system upgrades, security patches, or worrying about server uptime. Your focus shifts entirely to your application code. Automatic scaling. Serverless applications scale automatically and almost infinitely in response to demand. If your application suddenly experiences a massive surge in traffic, the cloud provider instantly scales up the necessary resources to handle it. When demand drops, resources scale back down, often to zero. This elasticity guarantees performance during peak loads without over-provisioning and wasting resources during quiet periods. Pay-per-execution. With serverless, you generally pay only for the compute time and resources your code actually consumes. If your function runs for 50 milliseconds and uses 128 megabytes of memory, you pay for precisely that. There's no charge for idle time. This contrasts sharply with traditional models where you pay for servers that run continuously, regardless of whether they're actively processing requests. High availability and fault tolerance built in. Because the cloud provider manages the underlying infrastructure, serverless services are inherently designed for high availability and fault tolerance. They typically distribute your application across multiple availability zones within a region, ensuring that a localized outage won't take your entire application offline. Event-driven, serverless applications are fundamentally reactive. They don't typically run continuously, but instead spring to life in response to specific events. These events can be anything from an HTTP request coming through an API gateway, a new image being uploaded to an object storage service, a message landing in a queue, a change in a database, or even a scheduled time interval. This event-driven nature encourages a highly decoupled and asynchronous architectural style. Beyond FAS, while functions are foundational, a truly serverless application leverages a broader ecosystem of fully managed services. This includes serverless databases that scale on demand, like DynamoDB or Aurora Serverless, messaging queues like SQS, and publish-subscribe services like SNS. API gateways that manage incoming requests, object storage like S3 for vast amounts of data, and orchestration services like step functions that define complex workflows. It's the combination of these specialized, managed services that defines the full potential of serverless, allowing developers to build robust, scalable systems without ever touching a server. The compelling benefits of adopting serverless. The characteristics described above translate into tangible advantages that make serverless a highly attractive option for modern application development. Reduced operational overhead. By offloading infrastructure management to the cloud provider, development teams can significantly reduce the time and effort spent on operational tasks. This frees up engineers to focus on higher value activities, building features, solving business problems, and innovating. It's not about being operations-free, but operations-light. Faster time to market. With less time spent provisioning and managing infrastructure, and more time focused on writing application logic, development cycles can accelerate. Developers can quickly prototype ideas, deploy minimum viable products, and iterate rapidly, leading to a quicker response to market demands and customer feedback. Cost efficiency, when designed well. The pay-per-execution model can lead to substantial cost savings, especially for applications with fluctuating or unpredictable demand. Instead of paying for always-on capacity to handle peak loads, you only pay for the actual computation time consumed. For instance, a small startup might see dramatic savings by building its initial services on a serverless model, avoiding large upfront infrastructure investments and paying only for what its few initial users consume. As the user base grows, the costs scale proportionally and efficiently. Inherent scalability and resilience. The unparalleled automatic scaling capabilities mean your application can effortlessly handle surges in traffic without manual intervention. This built-in elasticity also contributes to high availability. If a component fails, the cloud provider's managed services seamlessly shift workloads to healthy resources, often without you even noticing. Improved developer experience. For many developers, serverless offers a more focused and less distracting environment. The abstraction of infrastructure means a significant reduction in the cognitive load associated with servers, networking, and operating systems. This allows developers to concentrate on what they do best, writing code that delivers business value. Understanding the challenges and considerations. While the benefits are compelling, it's crucial to approach serverless with an understanding of its unique challenges. No technology is a silver bullet, and serverless architectures come with their own set of considerations. Vendor lock-in concerns. By relying heavily on specific cloud provider services, like Lambda, DynamoDB, or step functions, applications can become tightly coupled to that vendor's ecosystem. While the underlying patterns we discuss in this book are often cloud-agnostic, their implementation usually involves specific services. Managing vendor reliance means focusing on architectural principles that allow for portability if truly needed, or strategically leveraging the strengths of a chosen cloud provider. Cold starts. When a serverless function hasn't been invoked for a while, it might become inactive. The first time it's invoked after a period of inactivity, the cloud provider needs to initialize its environment, download the code, set up the runtime, etc. This initialization process can introduce a small latency, commonly known as a cold start. While often negligible for backend processes, it can be noticeable for latency-sensitive applications like interactive APIs. The choice of programming language, runtime, and clever design patterns can help mitigate these effects. Debugging and monitoring complexity. In a highly distributed, event-driven environment where functions are ephemeral and state is externalized, tracing a request through multiple services can be challenging. Standard debugging tools designed for monolithic applications often fall short. This necessitates robust observability strategies, focusing on centralized logging, comprehensive metrics, and distributed tracing. This is a topic so critical that we dedicate an entire chapter to it. Local development and testing. Replicating a full serverless environment, complete with all its managed services and event triggers, on a local development machine can be difficult. Developers often rely on cloud-based testing or specialized tools that emulate cloud services, which adds a layer of complexity to the development workflow. Security implications. While the cloud provider manages the security of the cloud, you remain responsible for security in the cloud. This includes configuring appropriate permissions for your functions, securing your data in serverless databases, managing secrets securely, and implementing robust authentication and authorization for your APIs. Understanding the shared responsibility model for security is paramount. Why design patterns are essential for serverless success. Given the unique characteristics and challenges of serverless computing, merely lifting and shifting traditional application designs won't cut it. Trying to build a typical monolithic application on serverless functions is an anti-pattern often referred to as monolith in a Lambda. This is where design patterns become invaluable. Just as architects use blueprints to design buildings and chefs use recipes to create dishes, software engineers use design patterns to solve common, recurring problems in a proven, efficient manner. In the context of serverless, patterns provide structured solutions. They offer well-tested ways to handle concurrency, data consistency, communication between decoupled services, error recovery, and more in an inherently distributed landscape. A common language, they establish a shared vocabulary for architects and developers, allowing for clearer communication and understanding of complex system designs. Guidance on best practices. They embody the accumulated wisdom of many successful serverless implementations, helping you avoid common pitfalls and leverage the platform's strengths. Maintainability and scalability. By applying proven patterns, you build systems that are not only capable of scaling to immense levels, but are also easier to understand, debug, and evolve over time. These patterns don't just tell you what to build. They teach you how to think about serverless applications. They bridge the gap between understanding individual serverless components and designing a truly cohesive, robust, and performant serverless architecture. By moving beyond simple functions and embracing these architectural patterns, you can unlock the full potential of serverless computing, transforming how you build and deliver modern cloud applications. The rest of this book will guide you through these powerful blueprints, empowering you to architect for the future. Chapter 2: Core Serverless Building Blocks, Functions, Events, and Services. In the previous chapter, we explored the revolutionary nature of serverless computing, understanding its fundamental shift from managing infrastructure to focusing on business logic. But a revolution doesn't happen with abstract principles alone. It requires powerful tools. This chapter delves into the core building blocks, the foundational services and concepts that empower serverless architectures. Think of these as the individual bricks, pipes, and wires that you'll use to construct your sophisticated serverless applications. Understanding how they function independently, and more importantly, how they interoperate, is crucial before we dive into the architectural patterns that combine them. The atom of serverless, functions as a service, FaaS. At the heart of the serverless paradigm lies the function as a service, or FaaS. These are the small, nimble units of code that encapsulate your application's logic. What is a serverless function? A serverless function is essentially a single-purpose piece of code that you provide to a cloud provider. It could be written in a variety of programming languages, such as Python, Node.js, Java, C#, or Go. What makes it special is that you don't worry about where it runs, how much memory it needs to start, or when it stops. The cloud provider handles all of that. It's designed to be invoked on demand, perform a specific task, and then shut down. The event-driven invocation model. Functions don't run continuously, they are reactive. They spring to life in response to an event. An event could be an incoming HTTP request from a web browser, a new image uploaded to an online storage system, a message arriving on a queue, a change detected in a database, or even a scheduled time tick. When that event occurs, the cloud provider creates an execution environment, runs your function code, and then tears down or recycles that environment. This on-demand nature is a major contributor to the cost efficiency and scalability of serverless. Statelessness explained. A fundamental characteristic of serverless functions is their statelessness. This means that a function does not retain any memory or data from one invocation to the next. Every time a function is triggered, it starts fresh, as if it has never run before. This design choice is critical for several reasons. Massive scalability. Because each invocation is independent, the cloud provider can effortlessly run tens, hundreds, or even thousands of instances of your function simultaneously to handle spikes in demand. There's no shared state that could become a bottleneck. Increased reliability. If an instance of your function fails, it doesn't affect subsequent invocations. A new, clean instance can simply be brought up to handle the next event without relying on the integrity of a previous one. Simplified management. You don't need to worry about session management or sticky sessions. All necessary information must either be passed in with the event or retrieved from an external, persistent data store. While this makes functions powerful and scalable, it also means that any persistent data, like user profiles, shopping cart contents, or processed image metadata, must be stored externally in specialized services. Functions are thus the compute engines, but they rely on other services for state. The triggers, how functions come alive, event sources. Functions are passive until an event brings them to life. These events originate from various event sources, which are effectively the triggers for your serverless functions. A HTTP API gateway. This is often the entry point for web, mobile, and third-party applications. An API gateway acts as a traffic controller and an intelligent front door for your backend services. When a user accesses an endpoint, say a website URL or a mobile app calls an API, the API gateway can receive that HTTP request, perform authentication and basic validation, and then trigger a serverless function. It can also route requests to different functions or even other services based on the incoming path or method. Think of it as a hotel's front desk, directing guests to the correct room, your function, based on their reservation. B. Message queues, e.g., Amazon SQS, Azure Queue Storage, Google Cloud Pub Sublite. Message queues provide a reliable way for different parts of an application to communicate asynchronously. When one service needs to send a message to another without waiting for an immediate response, perhaps to process a large file in the background or to send an email notification, it places the message onto a queue. A serverless function can then be configured to automatically poll and process messages from this queue. This decouples services, allows for buffering of messages during peak loads, and ensures that messages are processed even if the consumer function is temporarily unavailable. It's like sending a letter through the postal service. You drop it in the mailbox, and the postal service ensures it eventually reaches its destination, even if the recipient isn't home right away. C. Publish subscribe, e.g., Amazon SNS, Azure Service Bus Topics, Google Cloud Pub Sub. The publish subscribe model is designed for broadcasting messages to multiple recipients who are interested in a particular topic. A publisher sends a message to a topic, and all subscribers to that topic receive a copy of the message. This is highly effective for scenarios where one event needs to trigger several different, independent actions. For example, a new user registration might trigger one function to send a welcome email, another to update user statistics, and a third to provision initial user resources. It's like a public announcement system. One message is broadcast, and everyone tuned into that channel hears it. D. Object storage events, e.g., Amazon S3 events, Azure Blob Storage events, Google Cloud Storage events. Cloud object storage services are highly scalable and durable repositories for unstructured data like images, videos, documents, and backups. They can also act as powerful event sources. When a file is uploaded, deleted, or modified in an object storage bucket, it can automatically trigger a serverless function. This is commonly used for automated image processing, e.g., resizing images upon upload, data ingestion pipelines, or triggering analytics jobs when new data files arrive. E-database streams, e.g., Amazon DynamoDB streams, Azure Cosmos DB change feed. Many NoSQL databases now offer a stream or change feed capability. This exposes a chronological, ordered sequence of every change made to the data in the database. A serverless function can subscribe to this stream and react to real-time data modifications. This is incredibly powerful for scenarios like building audit logs, maintaining materialized views, updating search indexes, or replicating data to other systems in near real time. F. Scheduled events and event buses, e.g., Amazon Event Bridge Cloud Watch events, Azure Event Grid, Google Cloud Event Arc. Sometimes you need functions to run at specific intervals, like a traditional cron job. Scheduled events allow you to trigger functions on a regular timetable, every minute, hour, day, or even specific dates. Beyond simple scheduling, event buses provide a centralized way to route events from various sources, your applications, SaaS applications, or other cloud services to various targets, including your functions. They act as a sophisticated switchboard, matching events to interested consumers based on predefined rules, enabling highly decoupled architectures. Where data lives. Serverless storage services. As we discussed, serverless functions are stateless. This means that any data that needs to persist across invocations, or that needs to be accessed by multiple functions, must be stored in external, managed data services. The cloud provides a rich set of options, each optimized for different data types and access patterns. A. NoSQL databases, e.g., Amazon DynamoDB, Azure Cosmos DB, Google Cloud Firestore. These are highly scalable, distributed databases that don't rely on the traditional relational model. They are perfect for serverless applications because they are managed, scale on demand, and offer flexible schema models, making them ideal for handling large volumes of unstructured or semi-structured data with low latency. They are often the go-to choice for storing application state, user profiles, or configuration data. B. Object storage, e.g., Amazon S3, Azure Blob Storage, Google Cloud Storage. Often referred to simply as cloud storage, these services provide highly durable, available, and cost-effective storage for vast amounts of unstructured data. Think of them as virtually limitless hard drives in the cloud. They are used for storing images, videos, logs, data backups, and static website content. As mentioned, they are also powerful event sources. See relational databases, e.g., Amazon Aurora Serverless, Azure SQL Database Serverless, Google Cloud SQL. While NoSQL databases are excellent for many serverless use cases, some applications still benefit from the structured nature and transactional consistency of traditional relational databases. Serverless versions of these databases automatically scale their compute capacity up and down based on demand, and you only pay for the capacity consumed. This allows you to leverage the power of SQL with the benefits of serverless elasticity. Orchestrating complexity, workflow, and integration services. As serverless applications grow, they often involve multiple functions and services working together in sequence, in parallel, or with conditional logic. Managing these complex interactions can become challenging manually. This is where dedicated orchestration and integration services come in. A-step functions, e.g., AWS step functions, Azure Logic Apps, Google Cloud Workflows. Workflow services like step functions allow you to define and manage multi-step application workflows visually, as state machines. You can choreograph sequences of serverless functions, database operations, and other services. They handle retries, error handling, parallel execution, and manage the state of the workflow as it progresses. This provides a robust way to build complex, long-running processes common in distributed systems without writing custom orchestration code. Think of it as a conductor leading an orchestra, ensuring each instrument, function, or service plays its part at the right time, in the correct sequence, and gracefully handles any unexpected hiccups. B. Advanced integration services. Beyond explicit workflow management, other services facilitate communication and integration. This includes managed API services that connect to legacy systems, or services that allow you to define rules for routing messages between disparate systems, ensuring that your serverless components can interact seamlessly with each other and with external systems. Securing the serverless ecosystem. Identity and access management, IAM. Security is paramount in any cloud application, and serverless is no exception. Cloud providers offer robust identity and access management, IAM, services to control who or what can access which resources and perform which actions. The foundation of cloud security. IAM is the cornerstone of cloud security, allowing you to define granular permissions. For example, you can specify that only a certain serverless function can write data to a specific database table, or that only authorized users can invoke a particular API endpoint. B. Principle of least privilege. A critical security principle, especially in serverless, is the principle of least privilege. This dictates that every user, service, or function should only be granted the minimum necessary permissions to perform its intended task, and no more. If a function only needs to read from a specific object storage bucket, it should not be granted write access to that bucket, nor any access to sensitive databases. This minimizes the blast radius if a component is ever compromised. See roles for functions. Serverless functions typically operate under an execution role defined in IAM. This role dictates what other cloud services the function itself is permitted to interact with. When your function is invoked, it temporarily assumes this role, gaining the necessary credentials to perform its authorized actions. This ensures that every interaction your function has with other services is explicitly controlled and logged, bringing it all together, a simple serverless flow. Now that we've explored the individual building blocks, let's bring them together with a simple, illustrative scenario to see how they interoperate. Imagine you're building a service that processes newly uploaded profile pictures for a social media application. When a user uploads a new image, you want to automatically resize it, add a watermark, and update the user's profile with the new picture's location. Here's how a serverless flow might handle this. The trigger. A user, using their web or mobile application, uploads a new profile picture. This image is directly uploaded to an object storage bucket, like Amazon S3, a service designed for storing large files reliably. The event. As soon as the image file lands in the designated part of the object storage bucket, the service automatically emits an object storage event, an S3 object created event, for instance. This event contains details about the newly uploaded file, such as its name and location. The function invocation. This object storage event is configured to directly invoke a specific serverless function, our Lambda function. The details of the event are passed to the function as input. The function's work. The serverless function then wakes up. It reads the event information to identify the newly uploaded image. It then accesses the object storage bucket to retrieve the raw image file. Inside the function, the image processing logic executes. It resizes the image to various dimensions, applies a watermark, and perhaps optimizes its format. Storing processed data. Once processed, the function uploads the newly resized and watermarked image files back into the object storage bucket, perhaps into a different subfolder. Updating metadata. Concurrently, the function needs to update the user's profile to reflect the new image. It constructs a data update request and interacts with a NoSQL database, like DynamoDB, to modify the user's profile record, pointing to the new image's location in object storage. Secure access. Throughout this process, the serverless function's IAM role ensures that it has precisely the correct permissions: to read from the original image bucket, to write to the processed image bucket, and to update specific records in the NoSQL database. Without these permissions, the function's actions would be denied. In this verbal walkthrough, you can see how individual serverless components, object storage, events, functions, IAM, and NoSQL databases, collaborate to achieve a business goal. No servers were provisioned or managed, scaling was automatic, and payment was only for the actual computation and storage used. Conclusion: the serverless paradigm is built upon a robust ecosystem of managed services, each playing a specific role in an application's architecture. Understanding the foundational concepts of serverless functions, the diverse array of event sources that trigger them, the specialized data storage services that hold application state, and the orchestration tools that bind them together, all secured by granular access controls, is the essential first step. While this chapter lays out the individual components, the real art and power of serverless architecture come from combining these building blocks strategically using established design patterns, which we will begin to explore in the next chapter. Chapter 3, Designing for Serverless, Principles and Best Practices. Having explored the fundamental building blocks of serverless computing, it's time to shift our focus from individual components to the architectural mindset required to assemble them effectively. Designing for serverless isn't merely about coding functions. It's about embracing a new set of principles that maximize the benefits inherent in this paradigm while mitigating its potential pitfalls. This chapter lays out the foundational principles and best practices that underpin successful serverless architectures, setting the stage for the specific design patterns we will explore in subsequent chapters. Embrace the event-driven architecture, EDA. The most fundamental shift in serverless design is the embrace of event-driven thinking. Unlike traditional request-response models, where services tightly couple by making direct calls to one another, serverless thrives on asynchronous, event-based communication. The power of asynchronous communication. In an event-driven world, services don't call each other directly. Instead, they publish events to a central event bus or message queue. Other services, which are interested in those events, consume them asynchronously. This offers several powerful advantages. Loose coupling. Services become independent. A producer of an event doesn't need to know who the consumers are or even if they exist. This makes systems more resilient. If a consumer goes down, the producer isn't affected, and the event can be processed when the consumer recovers. Scalability. Each service can scale independently based on its specific workload without impacting others. Resilience. Failures in one part of the system are isolated. Events can be retried, and dead letter queues can capture failures for later analysis. Flexibility. It's easier to add new features or modify existing ones without disrupting the entire system. New consumers can simply subscribe to existing events. Identify your events, not just your APIs. Start by identifying the significant facts or changes of state within your system that other parts of the application might care about. These are your events. For example, instead of thinking, I need an API to process an order, think, when an order-placed event occurs, what happens next? This shifts your focus from imperative commands to reactive processes. Core architectural principles. Several architectural principles, while applicable to distributed systems generally, take on heightened importance and are elegantly supported by the serverless model. Statelessness and externalizing state. As discussed in Chapter 2, serverless functions are designed to be stateless. This is a critical principle for scalability and resilience. Any data that needs to persist across invocations, or that is shared between functions, must reside in an external, managed service. Best practice: never store session state, temporary data, or user information directly within the function's memory or file system. Instead, rely on services like NoSQL databases, DynamoDB, object storage, S3, or caching layers. Benefit: this allows your functions to scale horizontally and independently. A function instance can be spun up or down at any moment without affecting the integrity or continuity of user sessions or transactions. B. Idempotency: handling retries gracefully. In distributed, asynchronous systems, network issues, service unavailability, or timeouts can cause operations to fail or appear to fail, leading to retries. Idempotency means that performing the same operation multiple times with the same input produces the same result as performing it once. Best practice: design your functions and the operations they perform to be idempotent. This often involves using unique identifiers. Pass a unique transaction ID or message ID with each request. Checking for prior processing. Before performing an action, check if it has already been completed using the unique ID, e.g., if this order ID is already processed, do nothing. Conditional updates. Leverage database features like conditional writes, e.g., only update if the current version is X. Benefit: idempotency is crucial for guaranteeing data consistency in the face of inevitable retries, preventing duplicate transactions or corrupted data. Imagine an anecdote where a customer is charged twice for the same order because a payment function wasn't idempotent, a painful lesson learned. See least privilege access. Security is paramount. The principle of least privilege dictates that every component, function, user, service should be granted only the minimum permissions necessary to perform its specific task, and no more. Best practice: create fine-grained IAM roles for each serverless function. For example, a function that reads from a certain database table should not have write access to that table, nor any access to other tables or services it doesn't need. Benefit: this significantly reduces the blast radius or potential damage if a function or service account is compromised. It's a foundational security measure. D. Embrace managed services. The core philosophy of serverless is to offload undifferentiated heavy lifting to the cloud provider. This means embracing managed services for everything from databases to messaging queues, authentication, and logging. Best practice: whenever possible, choose a fully managed service over building or managing your own solution, e.g., use DynamoDB instead of self-hosting a database on EC2 instances. Use SNS SQS instead of self-hosting Kafka. Benefit: reduces operational burden, improves scalability, reliability, and security, and allows your team to focus on core business logic. III. Operational considerations for serverless design. While serverless reduces direct operational burden, it introduces new considerations related to the distributed nature of applications. A. Observability first. In distributed, event-driven systems, traditional debugging methods often fall short. You can't just attach a debugger to a running server. Observability, the ability to understand the internal state of a system by examining the data it produces, logs, metrics, traces, becomes crucial. Best practice: structured logging. Ensure your functions emit well-structured, contextual logs, e.g., JSON format, that include correlation IDs for tracing requests across multiple functions, timestamps, and relevant event data. Metrics: instrument your code to emit custom metrics for key business processes and performance indicators. Distributed tracing. Utilize tracing tools like AWS X-Ray to visualize the flow of requests and events across multiple serverless components, making it easier to pinpoint latency issues or failures. Benefit: enables rapid troubleshooting, performance optimization, and deep insights into application behavior. B. Cost optimization thinking. The pay-per-execution model needs careful consideration. While small applications can be incredibly cheap, poorly designed serverless architectures can become surprisingly expensive. Best practice: right-sizing functions. Configure function memory and CPU appropriately for their workload. Too little means slow execution. Too much means wasted money. Minimize invocations, designed to reduce unnecessary function invocations. Can a batch process combine multiple events? Efficient data processing. Process data close to its source, e.g., filter events before invoking a function. Stateless operations. Avoid logic that tries to maintain state in functions, as it often leads to anti-patterns that increase costs. Benefit. Ensures that the economic benefits of serverless are fully realized. See resilience and error handling. In a distributed system, failures are inevitable. Designing for resilience means anticipating and gracefully handling these failures. Best practice: retries and dead letter queues, DLQs. Configure automatic retries for functions and process events from queues. Implement DLQs to capture messages that fail repeatedly, allowing for manual inspection and reprocessing. Circuit breakers. For outward calls from functions to other services, consider implementing circuit breaker patterns, though often managed services like API gateways contribute here to prevent cascading failures. Timeouts and fallbacks. Set appropriate timeouts for functions and for external service calls. Implement fallback mechanisms for critical operations. Benefit: ensures that your application remains highly available and recovers gracefully from transient or permanent failures. IV, designing for deployability and evolution. Serverless architectures, often composed of numerous small, independently deployable units, require specific approaches to deployment and evolution. A. Infrastructure as code (ISC). Manual configuration of cloud resources is error-prone and doesn't scale. Infrastructure as code, using tools like AWS CloudFormation, Serverless Framework, AWS SAM, Terraform, allows you to define your entire serverless application's infrastructure, functions, API gateways, databases, permissions in code. Best practice: treat your infrastructure definitions like application code. Version control, peer review, and automate deployment through CI/CD pipelines. Benefit: ensures consistency, repeatability, rapid provisioning, and simplifies change management. B. Versioning and rollbacks. The independent nature of serverless components means changes can be deployed frequently. How do you manage updates and potential issues? Best practice: utilize service versioning capabilities, e.g., Lambda versions aliases. This enables safe deployments, e.g., canary deployments, gradual rollouts, and immediate rollbacks to previous working versions if issues arise. Benefit: reduces the risk associated with deployments and allows for rapid iteration and experimentation. See granular function design, single purpose. While not a strict rule, the common guidance is to keep functions small and focused on a single responsibility. Best practice: design each function to do one thing and do it well. For example, one function to process an order, another to send an email, another to update inventory. Benefit: improves testability, maintainability, and allows for independent scaling and deployment of components. This also helps in right-sizing resources, as a focused function typically requires less memory and processing time. Conclusion: designing for serverless is fundamentally about adopting a distributed, event-driven mindset. It requires a conscious effort to embrace statelessness, ensure idempotency, prioritize security through least privilege, and heavily leverage the powerful managed services provided by the cloud. Furthermore, a shift towards proactive observability, cost-aware design, robust error handling, and automated infrastructure management is crucial for long-term success. These principles form the bedrock upon which resilient, scalable, and cost-effective serverless applications are built. In the following chapters, we will dive into specific, proven design patterns that embody these principles, showing you how to apply them to solve common architectural challenges in the serverless world. Chapter 4: The Fan-Out Pattern, Distributing Workloads. In the realm of distributed systems, it's a common scenario. One event occurs, and that event needs to trigger multiple, often independent, actions or processes. Imagine a user signs up for a new service. This single action might need to trigger sending a welcome email, updating an analytics dashboard, notifying a sales team, and provisioning initial user resources. How do we orchestrate these parallel activities efficiently, scalably, and robustly in a serverless environment. The fan-out pattern provides an elegant solution. What is the fan-out pattern? At its core, the fan-out pattern is about taking a single input event or message and distributing it to multiple consumers simultaneously. It's not just a one-to-many relationship. It's specifically designed to enable concurrent, decoupled processing of that single event by various independent components. Think of it like a public address system at an airport. A single announcement, the input event, goes out, and multiple individual speakers in different gate areas, the consumers, simultaneously broadcast that message. Each speaker receives the same announcement, but they are independent units, and if one speaker goes out, the others continue to function. Similarly, in an application, one piece of data or one change in state initiates a series of parallel, distinct operations. The problem it solves in serverless. The serverless paradigm, with its emphasis on small, single-purpose functions, is naturally suited to this pattern. The fan-out pattern explicitly addresses several critical challenges. Scalability and performance. Instead of a single, potentially large and complex serverless function trying to perform all subsequent actions sequentially, fan-out breaks down the work into smaller, parallel tasks. This allows for much faster overall processing by leveraging the inherent concurrency of serverless. Decoupling. It ensures that the component generating the initial event, the publisher, doesn't need to know anything about the components that consume it, the subscribers. Publishers just send the event to a central distribution point. This separation of concerns means that you can add new consumers, modify existing ones, or even remove old ones without impacting the producer or other consumers. Resilience. If one of the downstream consumers encounters an error or temporarily fails, it affects only that particular process. The other consumers continue to process their respective tasks seamlessly. The overall system remains robust, preventing a single point of failure from cascading throughout the application. How it works in serverless. Implementing the fan-out pattern in a serverless architecture typically involves three key components. Event source publisher. This is where the initial event originates. It could be an API gateway triggering a serverless function, an object storage service detecting a new file upload, or a database stream noting a data change. Distribution hub. This is the core of the fan-out. It receives the single event and reliably delivers copies of it to all interested consumers. In serverless, these are typically fully managed messaging services that handle the broadcasting logic. Consumers. These are the serverless functions or other services that subscribe to the distribution hub and perform a specific, independent task based on the event. Let's look at common serverless implementations. Scenario 1. Simple notification and broadcast using a publish-subscribe service. This is perhaps the most straightforward and common implementation of fan-out, often using services like Amazon's Simple Notification Service, SNS, or similar offerings from other cloud providers. Flow, an initial action, e.g., a user submitting a form that invokes a serverless function, generates a message. This function then publishes that message to a publish-subscribe topic, an SNS topic. Multiple different serverless functions or message queues can subscribe to this topic. When the topic receives a message, it immediately broadcasts a copy of that message to all its active subscribers. Verbal example. Consider a customer relationship management system. When a new lead-generated event is identified, instead of a single serverless function trying to do everything, it sends a simple message to a central lead events topic. This topic then fans out that message. One subscribing serverless function processes it to send an immediate automated welcome email to the prospect. Another function takes the same message to update the sales manager's dashboard. A third function might push the lead's details into an external customer database. Each of these actions happens in parallel, completely independent of the others. Scenario 2. Event-driven routing with an event bus. For more sophisticated fan-out scenarios, especially when events need to be filtered or routed dynamically based on their content, an event bus, like Amazon Event Bridge, Azure Event Grid, or Google Cloud Event Arc, is an excellent choice. Flow, producers send descriptive events to the event bus. The event bus then uses predefined rules to filter and route events to specific targets, which can be serverless functions, message queues, workflow services, or other endpoints. These rules can inspect the event's data and direct it only to relevant consumers. Verbal example. Imagine a large logistics platform where numerous events occur. Shipment created, package scanned at hub, delivery attempted, etc. Instead of broadcasting every event to everyone, all these events are sent to a central event bus. The bus has intelligent rules. For instance, a shipment created event for an international order might be routed to a function that handles customs declarations and to a function that updates the global tracking system. A package scanned at hub event, however, might only be routed to the tracking system and the customer notification service. This allows for highly selective and efficient fan-out based on the specific type or content of the event. Scenario 3. Object storage event notifications for data pipelines. Cloud object storage often includes built-in capabilities to trigger serverless applications when files are created, updated, or deleted. This allows for a very natural fan-out of data processing tasks. Flow. A file is uploaded to an object storage bucket, e.g., an S3 bucket. The bucket is configured to send notifications to multiple destinations, e.g., several different serverless functions, or a single function that then publishes to a topic. Each configured destination receives an event notification containing details about the uploaded file. Verbal example. A photo-sharing application relies heavily on this. When a user uploads a high-resolution image to the cloud storage, that single upload event can simultaneously trigger one serverless function to generate a smaller thumbnail for display on mobile devices, a second function to extract metadata like location and camera type and store it in a database, and a third function to run image analysis to detect inappropriate content, all happening at the same time. Benefits of the fan-out pattern. Employing the fan-out pattern offers significant advantages in serverless application design. Massive parallelism. By distributing a single task into multiple independent subtasks, the overall processing time can be drastically reduced. This is crucial for high-throughput, low-latency applications. High decoupling and modularity. Components become highly independent. This means different teams can work on different consumers without impeding each other, and you can add new functionalities by simply adding a new consumer that subscribes to existing events without modifying the original producer. Enhanced scalability and resilience. Each consumer function can scale independently based on its specific workload. If one consumer experiences a temporary failure, the others are unaffected, ensuring that critical operations continue. The distribution hub also acts as a buffer and ensures guaranteed delivery or retries, further improving reliability. Extensibility. The highly decoupled nature makes the system extremely extensible. You can easily introduce new features or integrations simply by adding a new subscriber to an existing event stream without touching any of the existing code. Trade-offs and considerations. While incredibly powerful, the fan-out pattern is not without its considerations. Eventual consistency. When multiple consumers process an event asynchronously, the various downstream systems or data stores might not update simultaneously. This leads to eventual consistency, where the system's state converges over time. Developers must design their applications to handle this, perhaps by displaying pending status until all updates are complete. Complexity of coordination, if not managed. While the pattern promotes decoupling, if you need to aggregate results from all the fanned-out consumers, or if the order of operations among them matters, it can introduce new challenges that might require additional patterns, like the Saga pattern or specific workflow services, to manage. This is sometimes referred to as the fan-in problem. Monitoring and debugging. While the observability pattern, Chapter 9, will cover this in detail, it's worth noting that tracing a single business transaction that fans out across multiple independent functions can be more complex than tracing a linear flow. Robust logging, metrics, and distributed tracing are critical. Cost implications. More functions being invoked in parallel can mean more serverless invocations and potentially higher costs. However, this is usually offset by the performance gains and the efficiency of paying only for actual compute time. Careful design ensures that only necessary consumers are triggered. Real-world use cases. The fan-out pattern is fundamental to many modern serverless applications. Content processing pipelines. As discussed, parallel processing of images or videos, thumbnail generation, watermarking, metadata extraction, content moderation, upon upload. Real-time notifications. Sending SMS, email, mobile push notifications, and in-app alerts simultaneously upon a significant event. Data ingestion and transformation, ETL. Ingesting raw data and fanning it out for parallel processing, cleaning, enrichment, and loading into various data stores or analytics engines. User activity logging. Recording user actions, logins, purchases, searches, and fanning them out to multiple systems for analytics, archiving, and fraud detection. Conclusion. The fan-out pattern is a cornerstone of building scalable, resilient, and highly decoupled serverless applications. By intelligently distributing a single event to multiple, independent consumers, it leverages the inherent parallelism of the cloud to dramatically improve system performance and foster a modular, extensible architecture. While it introduces considerations like eventual consistency and the need for robust observability, its benefits in enabling efficient and robust distributed processing make it an indispensable tool in the serverless architect's toolkit. It serves as a powerful building block, often combined with other patterns we will explore to construct more sophisticated cloud-native solutions. Chapter 5. The Saga Pattern. Orchestrating distributed transactions. In the world of monolithic applications, managing transactions was relatively straightforward. A single database often handled all operations, and the ACID properties, atomicity, consistency, isolation, durability, ensured that a series of operations either all succeeded or all failed, leaving the system in a consistent state. But as we move into the realm of microservices and serverless architectures, where applications are composed of many independent, decoupled services, each potentially with its own dedicated data store, the concept of a single transaction that spans multiple services becomes a significant challenge. The problem: distributed transactions and the monolith chains. Imagine an e-commerce platform built as a serverless application. When a customer places an order, several distinct operations need to happen. Deduct the payment from the customer's account, update the inventory to reserve the items, create a shipping request, send a confirmation email to the customer. In a monolith, these might all be part of one large database transaction. If the payment failed, the entire transaction would roll back and no inventory would be reserved, no shipping request made. But in a distributed serverless environment, the payment service, inventory service, shipping service, and notification service are likely distinct entities, each with its own database. How do you ensure that if the payment fails, the inventory reservation is undone and the shipping request isn't accidentally created? You can't simply use a traditional two-phase commit across different databases and services in a scalable, performant way. This leads to the problem of distributed transactions. If one step fails, you need a mechanism to unwind or compensate for the actions that have already occurred in previously successful steps, maintaining consistency across the entire system. This is where the Saga pattern steps in, introducing the Saga pattern. The Saga pattern is a strategy for managing distributed transactions that lack a single ACID transaction manager. Instead of one global transaction, a Saga is a sequence of local transactions, where each local transaction updates its own database and publishes an event that triggers the next step in the Saga. If a local transaction fails, the Saga executes a series of compensating transactions to undo the changes made by the preceding successful local transactions. Think of it like a journey with multiple stops. Each stop is a local transaction. If you reach a stop and discover you can't proceed to the next, you must backtrack, performing compensating actions at each previous stop to return things to how they were, e.g., getting a refund, unreserving a hotel room. The Saga pattern embraces eventual consistency, meaning that at any given moment, the entire system might not be perfectly consistent, but it will eventually reach a consistent state as all local transactions and compensating transactions complete. How sagas work, the core concept. A saga is composed of several steps, each of which is a local transaction. Each local transaction has a corresponding compensating transaction. Successful path. If all local transactions succeed, the saga completes. Failure path. If any local transaction fails, the failed service attempts to roll back its own local transaction if possible. It then triggers the execution of compensating transactions for all previously completed local transactions in reverse order. These compensating transactions are designed to undo the effect of their corresponding forward local transaction. For example, in our e-commerce case, Step 1, process payment local transaction 1. If successful, publish payment approved event. If failed, publish payment failed event. Step 2, reserve inventory local transaction 2, triggered by payment approved event. If successful, publish inventory reserved event. If failed, publish inventory reservation failed event. If this fails, a compensating transaction must occur to refund the payment from local transaction 1. Step 3, create shipping request local transaction 3, triggered by inventory reserved event. If successful, publish shipping requested event. If failed, publish shipping request failed event. If this fails, compensating transactions must occur to unreserve inventory from local transaction 2 and refund payment from local transaction 1. Implementing sagas in serverless, orchestration versus choreography. There are two primary ways to coordinate the steps within a saga in a serverless environment. 1. Choreography-based saga. In a choreography-based saga, each service participates in the saga by publishing events, and other services react to those events. There is no central orchestrator. It's fully decentralized. How it works: serverless. A serverless function, e.g., invoked by an API gateway for a new order, performs its local transaction, e.g., storing order details, deducting payment. Upon completion, it publishes an event, e.g., order created event, payment approved event, to a messaging service like a publish subscribe topic (SNS) or an event bus (event bridge). Other serverless functions in distinct services, e.g., inventory service, shipping service, are subscribed to these events. When an event arrives, a subscribed function invokes its local transaction. If successful, it publishes its own success event. If it fails, it publishes a failure event, e.g., inventory reservation failed event. Functions responsible for compensating transactions listen for these failure events and execute their undo logic. Verbal example. An order placed through an API gateway triggers a serverless function that handles the initial order creation and payment processing. If the payment is successful, this function emits a payment approved event onto a central event bus. The inventory service, a separate collection of functions, listens for payment approved events. Upon receiving one, it attempts to reserve items in its own database. If the reservation succeeds, it emits an inventory reserved event. If it fails, it emits an inventory reservation failed event. The payment processing function is also listening. If it sees an inventory reservation failed event, it triggers its own compensating transaction, initiating a refund to the customer. Meanwhile, the shipping service listens for inventory reserved events to create a shipment request. Pros: loose coupling. Services are highly independent and don't need to know directly about each other. Scalability: can scale easily as new services can subscribe to existing events without modifying existing components. Cons: complexity: harder to understand the end-to-end flow of the saga. Debugging can be challenging as the flow is implicit and spread across many services. Circular dependencies can sometimes lead to services directly or indirectly invoking each other in a loop if not designed carefully. No global view, difficult to get a clear picture of the overall saga's status at any given time. 2. Orchestration-based saga. In an orchestration-based saga, a central orchestrator component tells each service which local transaction to execute. The orchestrator maintains the state of the saga and determines the sequence of steps, including success paths and compensating transaction paths. How it works: serverless. A dedicated orchestrator service typically a serverless workflow service like AWS Step Functions, is used. The orchestrator defines the entire saga as a state machine, explicitly outlining each local transaction step, often implemented as serverless functions, and their corresponding compensating transactions. When the saga starts, the orchestrator invokes the first local transaction function. Upon completion, the orchestrator receives the result and, based on the success or failure, decides the next step, either the next forward local transaction or the appropriate compensating transaction. The orchestrator handles retries, timeouts, and manages the overall state of the saga. Verbal example. For the same order process, an initial serverless function, triggered by the API gateway after a customer places an order, initiates a order fulfillment step functions workflow. This workflow is now the central brain. It first invokes a function to process payment. If process payment reports success, the workflow then automatically invokes a separate function to reserve inventory. If reserve inventory succeeds, it then calls create shipping request. If any of these steps fail, the step function's workflow immediately jumps to a predefined failure branch. For example, if reserve inventory fails, the workflow directly invokes a refund payment compensating function, then logs the overall order as failed. The workflow keeps track of the entire order's journey, from start to finish, including any rollbacks. Pros: clear global view. The orchestrator provides a single place to view, manage, and debug the entire saga flow. Easier error handling, centralized error handling and compensating transaction logic, decoupling from business logic. The business logic for the saga itself resides within the orchestrator, making individual services simpler. Cons: centralization concerns. The orchestrator can become a single point of failure or a bottleneck, though managed services like step functions are highly resilient and scalable. Tighter coupling. Services are more tightly coupled to the orchestrator as they are explicitly called by it. Comparing orchestration and choreography. Choosing between orchestration and choreography for your saga depends on the specific needs of your application. Choose choreography when the saga is relatively simple with few steps. You need maximum decoupling and flexibility for future changes. The flow isn't highly complex and primarily involves services reacting to fundamental business events. Choose orchestration when the saga is complex with many steps, conditional logic, or parallel executions. You need a clear, explicit view of the overall transaction state. Error handling and compensating transaction logic need to be precisely managed. You are comfortable with a single component managing the flow, though this component should be a highly available managed service. In serverless environments, highly resilient managed services like step functions make orchestration a very attractive and often preferred choice for complex sagas due to the improved visibility and debugging capabilities they offer. Benefits of the saga pattern: data consistency in distributed systems. It provides a mechanism to achieve eventual consistency across multiple, independent services and their databases where traditional ACID transactions are not feasible. Enables microservices and serverless. It's a foundational pattern that allows breaking down monolithic applications into smaller, more manageable services by overcoming the distributed transaction problem. Improved scalability and resilience. By avoiding long-running distributed locks, sagas generally lead to more scalable and resilient systems. If one step fails, only the relevant compensating transactions are executed, rather than blocking the entire system. Trade-offs and considerations. Increased complexity. Sagas are inherently more complex to design, implement, and debug than single database transactions. Compensating transactions. Designing and implementing reliable compensating transactions is crucial. These compensating actions must also be idempotent, meaning they can be safely retried. Eventual consistency implications. Developers and users must understand that the system's state may not be instantly consistent across all services. User interfaces might need to reflect intermediate states, e.g., order pending, payment processing. Observability is key. As with any distributed pattern, clear logging, metrics, and tracing are essential to monitor the progress of sagas and diagnose failures. Real-world use cases. The saga pattern is essential for any multi-step business process spanning multiple services. E-commerce order fulfillment. The classic example, as discussed, placing an order, processing payment, reserving inventory, sending notifications, creating shipping requests. Travel booking. Reserving flights, hotels, and rental cars from different providers. If one fails, compensating actions cancel the others. Multi-step customer onboarding. Creating a user profile, setting up billing, provisioning resources, e.g., creating a dedicated storage bucket, and sending a welcome kit. Financial transactions. Complex money transfers involving multiple banks or accounts. Conclusion. The saga pattern is a powerful and necessary tool for building robust, consistent, and scalable applications in serverless and microservices architectures. By understanding its core concept, a sequence of local transactions with compensating actions, and choosing between choreography and orchestration, engineers can tackle the challenge of distributed transactions. While it introduces a degree of complexity, the ability to maintain data integrity across independent services makes the saga pattern an indispensable building block for modern cloud-native systems. Chapter 6. The Strangler Fig Pattern, Migrating Legacy Systems. In the world of software development, new technologies emerge at a rapid pace, promising greater efficiency, scalability, and resilience. Serverless computing offers precisely that, but for many organizations, the reality is a vast landscape of existing, often monolithic, applications. These legacy systems, while perhaps years or even decades old, frequently underpin critical business functions. Directly replacing or rewriting such a monolith from scratch is a high-risk, high-cost, and lengthy endeavor, often leading to project failures, budget overruns, and missed opportunities. This is where the strangler fig pattern emerges as a lifeline, offering a safer, incremental approach to modernizing legacy applications, including their migration to a serverless architecture. The problem: the monolithic migration maze. Imagine a deeply entrenched monolithic application that has evolved over many years. It contains tightly coupled functionalities, a single large codebase, and often a single, complex database schema. The thought of migrating this entire system to a new cloud-native, serverless architecture can be daunting. High risk of failure. Big bang rewrites are notorious for failing. They involve rebuilding a large system with all its complexities, and only at the very end can you determine if the new system truly matches the old system's functionality and performance. Business disruption. A complete rewrite means the existing application can't evolve significantly during the migration, potentially stifling new feature development. Cost and time. Such projects are typically expensive and lengthy, consuming significant financial and human resources without delivering incremental value until completion. Loss of knowledge. The intricacies and undocumented, tribal knowledge within an old monolith can be difficult to transfer to a new system, leading to unexpected behaviors or missed requirements. The strangler fig pattern provides an evolutionary alternative to this risky all-or-nothing approach. Introducing the strangler fig pattern. The strangler fig pattern, coined by Martin Fowler, draws its name from a species of fig tree native to tropical forests. These fig trees begin their life as small seedlings on a host tree. They then grow roots downwards from the canopy, eventually reaching the ground. Over time, these roots thicken and intertwine, slowly enveloping the host tree. Eventually, the fig tree might grow so large and dense that it strangles and outlives the original host, which decomposes within the new structure, leaving the fig tree standing in its place. In software architecture, the analogy is powerful. Instead of directly cutting down the old host, monolith, you incrementally build new functionalities around it. The new, serverless components gradually take over responsibilities from the old system. Over time, the new system strangles the old one by replacing its functionalities, piece by piece, until the monolith shrinks, atrophies, and eventually can be safely decommissioned. How it works in a serverless context. Applying the strangler fig pattern to serverless migration involves several key steps. 1. Identify a subdomain or feature to migrate. This requires careful analysis of the monolith to identify a relatively self-contained functionality or business subdomain that can be extracted. Look for areas with clear boundaries, frequent changes, or new feature development. 2. Introduce a facade proxy, the strangler. This is the crucial step. You don't refactor the monolith internally. Instead, you place a new service, often implemented using an API gateway, in front of the existing monolith. This API gateway acts as a traffic police, directing requests. Initially, all requests might flow through it directly to the monolith. 3. Build new functionality, or rewrite old, as serverless components. For the identified subdomain, you then incrementally build new serverless microservices that implement that functionality. These could be serverless functions, like AWS Lambda, interacting with serverless databases, like DynamoDB or other managed services. This new functionality will exist alongside the monolith. 4. Reroute traffic incrementally. Once a serverless component is ready to handle a particular part of the functionality, you reconfigure the API gateway to route requests for that specific functionality to the new serverless component instead of the monolith. This can be done gradually, perhaps routing just a small percentage of traffic initially or only for specific users before a full cutover. Verbal example. Imagine a large legacy e-commerce system that has grown organically over decades. It handles everything: product catalog, user authentication, order processing, shipping. We want to modernize its user authentication module. Instead of rewriting the entire system, we first place an API gateway in front of the existing monolith's authentication endpoints. Initially, all login requests coming through this new gateway are simply proxied directly to the monolith's old authentication code. Separately, we then build a new serverless authentication service using Lambda functions and a serverless identity provider. Once this new service is fully tested and robust, we update the API gateway's routing rules. From that point on, incoming login requests are no longer forwarded to the monolith. They are now directed to our new, blazing fast serverless authentication service. The old monolith's authentication code effectively starves because no traffic reaches it, but the monolith continues to serve all other functions as before. 5. Repeat and dismantle. You continue this process, iteratively identifying components, building serverless replacements, and routing traffic. Over time, more and more functionalities are strangled out of the monolith. As portions of the monolith become unused, they can be safely removed, simplifying the legacy codebase until, eventually, nothing remains of the original host application but the new cloud-native system. Benefits of the strangler fig pattern. Risk mitigation. This pattern significantly reduces the risk associated with large-scale modernization projects. You make small, incremental changes, allowing for continuous feedback and minimizing the impact of potential errors. Failed experiments can be quickly rolled back. Continuous delivery of value. New features or migrated functionalities are deployed incrementally, providing immediate business value rather than waiting for a distant, big bang release. Reduced scope and complexity. Each migration step is smaller and more manageable, making it easier for development teams to focus and deliver. Learning opportunity. Teams can learn and adapt to working with serverless technologies in a controlled environment, gaining experience without jeopardizing the entire system. Parallel operation. The old and new systems coexist, ensuring business continuity throughout the migration. Cost efficiency. You only build and pay for the new serverless resources for the functionalities you are actively migrating, rather than provisioning a whole new duplicate system. Trade-offs and considerations. Initial overhead. Introducing the proxy API gateway layer upfront adds an initial architectural complexity and potentially a small performance overhead. But this is usually negligible compared to the benefits. Dual operation complexity. For a period, you will have two systems, the monolith and the new serverless components, running simultaneously. This requires careful management of data consistency, if shared, routing, and monitoring. Database migration. One of the trickiest aspects can be data. If the new serverless components need to read or write data that is currently owned by the monolith's database, you might need strategies like data lake replication, replicating data from the monolith's database to a new serverless-friendly data store. Shared database, temporary, allowing the new serverless components to temporarily share the monolith's database, with a plan to migrate data ownership to the new services eventually. API exposure. The monolith can provide an API for the new services to access necessary data. Identification of boundaries. Identifying truly independent subdomains within a tightly coupled monolith can be challenging and requires deep understanding of the business logic. Real-world use cases. The strangler fig pattern is immensely valuable for migrating legacy APIs, replacing old, monolithic API endpoints with new serverless-backed APIs, modernizing specific modules, extracting functionalities like user authentication, payment processing, notification services, or reporting from an aging monolith, adding new features to old systems. Instead of trying to bolt new functionality onto a complex, brittle monolith, build it as a new serverless service and route traffic to it. Refactoring a database, gradually shifting data ownership from a monolithic database to a distributed set of independent databases for each new microservice. A common application is when a company wants to launch a new mobile application that needs a modern, fast API, but all existing data and business logic are tied up in an outdated system. Instead of waiting for a full rewrite, the new mobile team can use the strangler fig approach. They build their new API backends with serverless functions, proxying only the specific calls they need through an API gateway to the old system initially, and then progressively replace those proxied calls with completely new serverless logic as they build it out. Conclusion: the strangler fig pattern offers a pragmatic, low-risk, and highly effective strategy for migrating legacy monolithic applications to modern, scalable serverless architectures. By avoiding the Big Bang approach and instead adopting a gradual, iterative process of building new functionalities around the old system and incrementally rerouting traffic, organizations can progressively transform their critical business systems. This pattern not only mitigates risk and ensures business continuity, but also accelerates the delivery of new features and capabilities, making the journey to serverless a much smoother and more successful one. Chapter 7. The Event Sourcing Pattern, Building Immutable Histories. In traditional application development, our primary focus is on storing the current state of an entity. When a customer changes their address, we update the address fields in the database. When a stock quantity changes, we decrement the quantity on hand field. This approach, known as state-based persistence, is simple and intuitive for many applications. However, it discards valuable information, the history of how the current state was reached. What if you needed to know the customer's previous addresses, or how the stock quantity changed over time, not just its current value? For many business domains, knowing the complete history of changes, the why and how things happened, is just as important, if not more so, than knowing the current state. This is where the event sourcing pattern offers a fundamentally different and powerful approach to data management. The problem: losing valuable history with state-based persistence. Consider a complex business process, like an order management system. If you only store the current state of an order, e.g., status, shipped, you lose the detailed narrative. When was the order placed? When was it picked? When was it packed? When was it dispatched? Were there any cancellations or returns within the order's life cycle? Each of these steps is an event that occurred. If you only store the final status, you've discarded the journey. Reconstructing this history for auditing, analytics, debugging, or even for deriving new insights becomes impossible or extremely difficult. Troubleshooting inconsistencies can also be challenging if you don't know the exact sequence of operations that led to a particular state. Introducing the event sourcing pattern. The event sourcing pattern fundamentally changes how we persist data. Instead of storing just the current state of an entity, we store the sequence of all state-changing events that have occurred to that entity. This immutable, chronological log of events becomes the primary source of truth. Think of it like an accounting ledger. You don't just store the current bank balance, you store every debit and credit transaction that led to that balance. To find the current balance, you sum up all the transactions. Similarly, with event sourcing, to get the current state of an entity, you replay all the events that have affected it from its beginning. Each event typically represents a discrete business fact that has happened in the past, e.g., order placed, customer address changed, item shipped, payment failed. These events are immutable. Once recorded, they cannot be changed or deleted. How event sourcing works in a serverless context. Implementing event sourcing in a serverless environment leverages the event-driven nature inherent in serverless architectures. Command and event generation. An external command, e.g., from an API gateway, an administrative interface, or another service, is received by a serverless function, often a Lambda function. This function represents the write model of your system. Instead of directly updating a traditional database row, the function validates the command and, if valid, generates one or more events that describe the change that just occurred. These events are facts, typically named in the past tense, e.g., payment processed, product added to cart. Event store, the immutable log. The generated events are then persisted in chronological order to a specialized event store. This event store is an append-only log that ensures events are stored durably and immutably. In a serverless environment, suitable technologies for an event store might include Amazon DynamoDB streams, a change data capture service built into DynamoDB, suitable for capturing changes to a DynamoDB table and propagating them as events. Amazon Kinesis streams data Firehose or Kafka on Confluent Cloud Amazon MSK. Scalable, ordered, append-only logs designed for high-throughput streaming data, ideal for serving as the central event store. Dedicated event store databases. Specialized databases optimized for event streams, though often cloud-native streaming services can serve this role effectively. Read models, projecting from events. Since querying the current state by replaying all events from scratch for every request is inefficient, the event sourcing pattern typically involves creating separate read models or projections. Other serverless functions, or sometimes dedicated services, consume events from the event store asynchronously. For each event, these functions update one or more denormalized read model databases, which are optimized for specific queries. This means different read models can exist for different querying needs. These read models can be stored in various serverless databases, such as DynamoDB for fast key-value lookups, Aurora Serverless for relational queries, or Elasticsearch for search queries. Verbal example. Let's trace a customer's order in a system using event sourcing. When a customer clicks Place Order, an API gateway invokes a serverless function. This function validates the order details but doesn't directly update an orders table. Instead, it creates an order-placed event, capturing details like customer ID, items, and initial timestamp. This event is then appended to an event store, perhaps a Kinesis stream configured as the immutable log. A separate set of serverless functions are constantly listening to this event store. One function might read order-placed events and update a denormalized orders summary table in DynamoDB, optimized for quickly showing a customer's current orders. Another function might take the same order-placed event and update a sales dashboard, optimized for analytical queries which might live in a separate database. Later, if the order is shipped, another API call invokes a different serverless function, which then generates an order shipped event and appends it to the same event store. The order summary function processes this order shipped event to update the order's status. Another function might use the order shipped event to send a customer notification. The key is that the event store contains all these immutable facts: order placed, order shipped, payment processed, etc. To know the current state of an order, you replay all these events in sequence. Benefits of the event sourcing pattern. Complete business history, auditability. Provides a comprehensive, immutable audit trail of all changes. This is invaluable for regulatory compliance, debugging, and understanding the evolution of entities over time. Time travel capabilities. You can reconstruct the state of any entity at any point in its history by replaying events up to that specific timestamp. This is powerful for forensics, bug reproduction, or analytics. Enhanced debugging and forensics. Because every state change is logged as a discrete event, diagnosing bugs or understanding why a system entered an inconsistent state becomes significantly easier. You can literally see the step-by-step evolution. Foundation for analytics and reporting. The stream of events represents a rich source of data for business intelligence and analytics. New aggregate views or reports can be generated retrospectively by consuming the event stream. Decoupling and scalability. Events are inherently immutable, promoting loose coupling between the system generating the event, the write side, and the systems consuming them, the read side or projections. Projections can be scaled independently of the event store and the write model. Resilience. If a read model becomes corrupted or needs to be rebuilt with new logic, you can simply discard it and regenerate it by replaying all events from the event store. Natural alignment with event-driven architecture. Event sourcing naturally fits within the broader, event-driven paradigm favored by serverless applications. Trade-offs and considerations. Increased complexity. Event sourcing is a more complex pattern to implement than traditional state-based persistence. It requires a different mindset and careful design of events, commands, and projections. Querying historical data. While simple forward replay is possible, complex queries about historical states, e.g., how many customers changed their address more than twice in the last year, can be challenging and might require specific analytical tools or dedicated historical projections. Data size. The event store can grow very large over time, as events are never deleted or modified. Strategies for archiving or snapshots might be necessary for very long-lived systems. Event schema evolution. Changes to event schemas over time, e.g., adding a new field to an order-placed event, require careful versioning and migration strategies to ensure old events can still be processed by new code. Initial learning curve. Developers accustomed to CRUD, create, read, update, delete, operations might find the event-centric approach challenging at first. Relationship with CQRS. Event sourcing is very frequently used in conjunction with the command query responsibility segregation, CQRS, pattern, which we will discuss in detail in the next chapter. CQRS enhances event sourcing by formalizing the separation between the write model, where commands are processed and events are generated, and the read models, where events are consumed to update optimized query structures. Real-world use cases. Event sourcing is particularly well-suited for domains where the history of changes is critical, or where complex business logic involves intricate sequences of events. Financial applications. Auditing every transaction for compliance and fraud detection, e.g., banking, trading platforms. Auditing and compliance. Any system requiring a complete, immutable record of every change, such as healthcare records or legal case management. E-commerce systems, tracking the full life cycle of an order, from placement to delivery, including returns and exchanges. Gaming, recording every player action, which can be replayed for debugging, cheating detection, or analytics. Internet of Things, IoT, storing sequences of sensor readings or device interactions. Collaborative editing, document management, maintaining versions and changes made to documents. Supply chain management, tracking goods through various stages from manufacturing to delivery. Conclusion. The event sourcing pattern represents a fundamental shift from storing current state to storing a complete, immutable history of events. In a serverless context, where event-driven architectures are a natural fit, event sourcing can provide unprecedented capabilities for auditing, debugging, time travel, and driving powerful analytics. While it adds a layer of conceptual complexity, the richness of the immutable event log and the flexibility it provides for generating diverse read models make it an exceptionally powerful pattern for building durable, highly observable, and insightful serverless applications, where knowing what happened is as crucial as knowing what is currently. Chapter 8. The CQRS pattern, separating read and write concerns. As applications grow in complexity and scale, their data access patterns often diverge significantly. The operations that modify data, commands, typically involve complex business logic, validation, and strict consistency requirements. In contrast, operations that retrieve data queries are often simpler, focusing on speed, flexibility in projection, and serving a high volume of requests. When both commands and queries operate on the same data model and database, a single solution often ends up being suboptimal for one or both types of operations. This is the problem addressed by the Command Query Responsibility Segregation (CQRS) pattern. It's a powerful architectural approach that separates the component responsible for processing commands, writing data, from the component responsible for processing queries, reading data. The problem: a single model for conflicting demands. In many traditional applications, a single data model and a single database handle both data modification and data retrieval. This unified model approach faces several challenges as applications scale. Conflicting requirements. Write operations need strong transactional consistency, complex validation, and often require normalized data models to reduce redundancy and ensure integrity. They might involve computationally intensive business logic. Read operations need high performance, low latency, and often require denormalized data models optimized for various display or reporting needs. They might serve many more requests than write operations. Performance bottlenecks. A database optimized for writes, e.g., highly normalized relational database with many joins, might be slow for complex reads, and vice versa. Scaling a single database to handle both high write and high read loads can be challenging and expensive. Complexity. A single model system can become overly complex as it tries to satisfy both read and write requirements, leading to bloated entities, convoluted queries, and difficult-to-maintain code. Security concerns. Granting read and write access to the same model can pose security risks. Often, users need to read more data than they are allowed to modify. Trying to optimize a single data model and a single database for these often conflicting requirements inevitably leads to compromises. Introducing the CQRS pattern. CQRS, short for Command Query Responsibility Segregation, is an architectural pattern that proposes a fundamental separation. Commands, operations that change the state of the system, e.g., create order, update customer address, process payment. These are typically imperative and modify data. Queries, operations that retrieve data from the system without changing its state, e.g., get product details, list customer orders, search invoices. These are typically declarative and read data. With CQRS, you use separate data models and often separate data stores for updates and reads. Write model, command side. This model is optimized for processing commands. It enforces business rules, performs validations, and ensures transactional consistency. It's designed to guarantee that the system's state changes correctly. Read models, query side. These models are optimized for querying. They can be highly denormalized, tailored specifically for fetching data for particular user interfaces or reports. You can have multiple distinct read models for different querying needs. Data synchronization between the write model and the read models is typically achieved through eventual consistency. After a command updates the write model, an event is published, and the read models asynchronously update themselves by consuming these events. How CQRS works in a serverless context. CQRS is a natural fit for serverless architectures due to their inherent event-driven and distributed nature. Command processing, write side, command. A user interaction or API call generates a command, e.g., add product to shopping cart. API gateway front door. The command enters the system, often via an API gateway. Command handler serverless function. A dedicated serverless function, e.g., AWS Lambda, acts as the command handler. This function receives the command, performs business logic, validation, and updates the authoritative write data store. Write data store. This database is optimized for transactional writes and strong consistency, e.g., a DynamoDB table or an Aurora serverless RDBMS. It holds the canonical, normalized state of your entities. Event generation and propagation. After successfully processing a command and updating the write data store, the command handler publishes an event, e.g., product added to shopping cart event, to an event bus or stream. This event signifies that a state change has successfully occurred. This is often done via database change data capture, like DynamoDB streams, or by directly publishing to an event stream, like Kinesis or a pub subservice. Query processing, read side. Query. A user requests data, e.g., get shopping cart contents. Query API, serverless function API gateway. A separate API endpoint backed by a serverless function receives the query. Query handler, serverless function. This function retrieves data directly from the dedicated read data store. Read data stores. These are databases specifically optimized for read performance. You can have multiple read models, each tuned for a different type of query or UI representation. Examples include another DynamoDB table, denormalized for specific read patterns, an Elasticsearch cluster for full-text search, a columnar database for analytical dashboards, even S3 for reporting, e.g., exporting processed data files, read model population, event consumption, separate serverless functions, often referred to as projectors or denormalizers, continuously consume events from the event stream. When an event arrives, these functions update their respective read models. For example, a product added to shopping cart event would trigger a projector function that updates a denormalized shopping cart summary table in the read database. Verbal example. Let's consider an order management system. When a customer places an order, the place order command arrives at an API endpoint, which triggers a serverless function on the right side. This function validates the order, deducts payment, and stores the canonical order details in a highly consistent, transactional database, perhaps a DynamoDB table specifically designed for write operations. Crucially, after the order is saved, an order-placed event is published to a Kinesis stream. Meanwhile, on the read side, a completely separate set of serverless functions are constantly listening to this Kinesis stream. One of these functions might be responsible for updating a customer dashboard summary read model. It receives the order-placed event, extracts relevant customer and order data, and then updates a highly denormalized view of the customer's recent activity in a separate DynamoDB table designed purely for fast reads. Another read-side function might take the order-placed event to update a sales team daily report in an Elasticsearch index, optimized for complex search queries by the sales team. When a customer wants to view their order history, or the sales team wants a daily report, their queries go to different API endpoints, which are handled by different serverless functions. These read-side query functions directly access the pre-optimized customer dashboard summary table or the sales team daily report index. They never touch the write-optimized transactional database. This means customer queries are blazing fast, and the complex write operations are completely isolated from them, ensuring our critical order processing pipeline remains performant and robust. Benefits of the CQRS pattern. Independent scaling. The read and write models can be scaled independently. If you have far more reads than writes, a common scenario, you can allocate significantly more resources to the read side, e.g., more read replicas, more powerful read database instances, without impacting write performance. Optimized performance. Each side can use a data model and database technology perfectly optimized for its purpose. Write models can be normalized for data integrity. Read models can be denormalized for specific high-performance queries. Flexibility and agility. It's easier to evolve the data models. Changes to the read model, e.g., adding a new report, do not typically affect the write model and vice versa. New read models can be added by simply replaying existing events. Improved security. Read models can potentially expose fewer fields or aggregate data, reducing the surface area for data breaches, and read-only versions can be deployed. Separation of concerns and simplicity. Each part of the system, command processing, query processing, event projection, is simpler and more focused, leading to more maintainable code. Complementary to event sourcing. CQRS works exceptionally well with event sourcing, as described in Chapter 7, where the write model persists events to an event store, and read models are built by projecting these events. Trade-offs and considerations. Increased complexity. CQRS is significantly more complex than a traditional CRUD, create, read, update, delete approach. It involves multiple data models, eventual consistency, and often an event bus, leading to more moving parts. Testing and debugging. Distributed systems inherently bring challenges, and CQRS, with its asynchronous nature and multiple data stores, can make tracing and debugging more difficult. Robust observability, logs, metrics, tracing, is crucial. Eventual consistency. Data on the red side may not be immediately updated after a write operation. Customers using the application might experience a slight delay before their changes are reflected. This needs to be communicated and managed through appropriate UX design, e.g., your order is being processed. Data synchronization. Ensuring reliable and consistent synchronization between the write store and all read stores is a critical responsibility. Learning curve. Adopting CQRS requires a different mindset from traditional relational database development, and teams will need time to adjust. Real-world use cases. CQRS is best suited for complex domains with high-performance requirements, where reads and writes have significantly different access patterns and scaling needs. It's overkill for simple, low-traffic applications. E-commerce platforms, high volume of product browsing reads, but fewer order placements, writes. Often, product catalogs are served from highly optimized read models. Financial trading platforms, real-time dashboards, reads, need to be extremely fast, while trade execution, writes, requires strong consistency and complex validation. Social media feeds. Building a user's personalized feed, complex, real-time read, is distinct from posting new content, right? IoT and sensor data. Ingesting massive streams of sensor data, high-volume writes, which then needs to be aggregated and queried for analytics purposes, high-volume reads, often with different query patterns. Real-time analytics dashboards. Writing operational data to a transactional store, and then projecting it into a separate analytical store for rapid dashboard queries. Conclusion. The CQRS pattern offers a powerful architectural tool for decoupling and optimizing the read and write concerns of complex, scalable applications. In a serverless environment, where event-driven architectures and the use of specialized managed services are common, CQRS provides a natural fit for building highly performant, flexible, and resilient systems. While it significantly increases architectural complexity and introduces the challenges of eventual consistency, the benefits in terms of independent scaling, optimized performance, and increased agility make it an indispensable pattern for tackling the most demanding serverless application requirements. It truly shines when combined with event sourcing, forming a formidable duo for building robust, event-driven systems with transparent histories. Chapter 9. The Observability Pattern. Monitoring serverless applications. Imagine building a complex, distributed clockwork mechanism inside a sealed black box. You can hear its gears whirring, but you can't see what's happening, where a cog might be jammed, or why it's running slow. This analogy perfectly describes the challenge of operating serverless applications without robust observability. In traditional monolithic applications, you might connect directly to a server, inspect logs on a single machine, or run a debugger to understand internal behavior. Serverless turns this on its head. Your code runs in ephemeral containers, potentially thousands of them, scattered across a cloud provider's vast infrastructure. Components communicate asynchronously via events and queues. When something goes wrong, a function times out, a message gets stuck, or a user reports an error pinpointing the root cause becomes a daunting task. The observability pattern is not a single architectural design, but a fundamental approach to building applications that are inherently understandable from the outside. It's about designing your serverless systems from the ground up to produce relevant, high-quality data, logs, metrics, and traces that allows you to answer questions about their internal state without having to ship new code or deploy new diagnostics. The problem, the black box of distributed serverless systems. The very benefits of serverless automatic scaling, managed infrastructure, and event-driven decoupled components contribute to operational complexity. Ephemerality. Functions are short-lived. They spin up, execute, and shut down, making it hard to capture their state in real time. Distribution. A single user request might trigger a cascade of hundreds of events across dozens of functions and managed services. Tracing an end-to-end flow is difficult. Asynchronicity. Many operations happen out of band, making it hard to correlate events and understand cause and effect relationships across the system. Vendor abstraction. While abstracting away servers, it also abstracts away visibility into the underlying infrastructure. You can't just SSH into a Lambda instance. Debugging challenges. Traditional step debugging is often impractical. You rely on what your application tells you about itself. Without an intentional approach to observability, you end up with a black box where you can see inputs and outputs, but understanding the journey in between is a dark art, leading to lengthy troubleshooting times, missed performance issues, and frustrated teams. Introducing the observability pattern. The observability pattern for serverless applications focuses on 3 pillars: logging, structured, contextual records of events and state within your application; metrics, aggregated numeric data points that represent the behavior and performance of your system over time; tracing, end-to-end visibility into the flow of a single request or transaction as it traverses multiple services and components. Together, these pillars provide a deep understanding of your application's health, performance, and behavior, enabling proactive monitoring, faster debugging, and better decision-making. How it works in serverless applications. Serverless platforms inherently provide some level of observability data. But to gain true insight, you must augment this with intentional design choices in your code and configuration using cloud-native tools. 1. Logging, the narrative of your application. Logs are the most common form of telemetry. They provide a narrative of what happened within your function or service. Cloud-native logging services. All major cloud providers offer centralized logging services, e.g., AWS CloudWatch logs, Azure Monitor logs, Google Cloud logging. Serverless functions automatically output their standard output error streams to these services. Structured logging, instead of just printing plain text, emit logs in a structured format, typically JSON. This allows logs to be easily parsed, searched, and analyzed by logging tools. Best practice. Include key-value pairs that provide context, requested, a unique identifier for the entire transaction passed between functions. Function name, the name of the executing function. Timestamp, when the log was generated. Level. Info, warn, error, debug. Message, a human-readable description. Event data, specific data relevant to the event, e.g., userid, orderid, error message. Centralized logging. Configure logs from all functions and services to flow into a single, centralized log management system. This allows you to search across your entire application and correlate events. Verbal example. Instead of simply printing order processed, your code would log something like timestamp, level, info, requested, ABC 123 Zis, function name, process order lambda, message, order successfully processed, orderid, ORD 54321, payment status, approved. This structured format means you can later search for all orderid ORD 54321 or filter for all info messages from the process order lambda function, much more effectively than just looking for keywords in plain text. 2. Metrics, the pulse of your system. Metrics are quantitative measurements of your system's performance and behavior over time. They are aggregated numerical values and are best for answering how many or how much questions. Automatic metrics. Serverless platforms typically provide built-in metrics for functions, such as invocation count, execution duration, error count, and throttles. Custom metrics. Beyond the built-in metrics, define and emit your own custom metrics for specific business or technical indicators important to your application. Best practice. Business metrics. Number of new users, orders placed, items added to cart, payments failed. Application metrics. Database read-write latency, external API call duration, cache hit-miss rates. Dashboards and alerting. Visualize metrics on dashboards to monitor system health at a glance. Set up alerts based on metric thresholds, e.g., alert if error rate exceeds 5% or if P99 latency is above 500 ms. Verbal example. While the cloud system automatically tracks how many times your process order lambda is invoked, you might create a custom metric called payment failed count. Each time an attempt to process a payment fails within your function, you increment this custom metric. This allows you to build a dashboard showing you, over time, the exact number of payment failures versus successes. and set an alarm if payment failures per minute suddenly spike significantly. 3. Tracing. The journey of a request. Tracing provides end-to-end visibility into the flow of a single request or transaction as it propagates through multiple serverless functions and managed services. Distributed tracing tools. Services like AWS X-Ray, Azure Application Insights, or Google Cloud trace automatically, or with minimal setup. Capture and visualize the service calls across your distributed application. Context propagation. The key to tracing is context propagation. A unique trace ID is generated at the start of a request and passed along to every subsequent service call, function invocation, database query, external API call, service maps, and timelines. Tracing tools use this context to build a visual service map showing which services are involved in a request, and a timeline showing the duration of each segment of the request. This helps pinpoint latency bottlenecks and error points across your entire system. Verbal example. When a customer initiates an order placement request, a unique tracid is stamped onto that request. This tracid is then automatically, or manually, if needed, passed to the process order lambda, then to the database call for inventory reservation, then to the payment processing service, and finally to the email notification function. If someone reports a slow order, you can search by their ordered or a requested, and the tracing tool presents a visual timeline. You can see at a glance that the process order lambda itself was fast, but the call to the external payment gateway took 5 seconds, making it the bottleneck. Without tracing, that 5-second delay would be a mystery buried within a sea of logs. Best practices for implementing the observability pattern. Start with business outcomes. What critical business processes do you need to monitor? What defines success or failure for those processes? This guides what metrics and logs are most important. Standardize telemetry. Agree on common logging formats, naming conventions for metrics, and how trace IDs are propagated across your organization. Automate data collection. Leverage cloud provider automation, e.g., Lambda automatically logs to CloudWatch logs. For custom metrics and traces, integrate SDKs as part of your application setup. Implement correlation IDs. This is vital. Ensure a unique ID accompanies every request and is passed to all downstream services. This allows you to filter and trace a single transaction across your entire distributed system. Instrument gradually. Don't try to log everything at once. Start with essential operational and business metrics, then iteratively add more instrumentation as you identify specific areas needing deeper insight. Alert on symptoms, not causes. Instead of alerting on CPU utilization of an internal service, a cause, alert on elevated latency for your user-facing API, a symptom that directly impacts customers. Treat telemetry as code. Manage your logging configurations, metric definitions, and alerting rules using infrastructure as code, ISC tools, just like your application code. This ensures consistency and reproducibility. Trade-offs and considerations. Cost. Collecting, storing, and analyzing large volumes of logs, metrics, and traces can incur significant cloud costs. Implement retention policies and filter out unnecessary data. Overhead. While usually minimal, instrumentation, especially extensive custom logging or tracing, can introduce a small performance overhead to your functions. Complexity. Designing and implementing a robust observability strategy for large serverless applications requires skill and effort. It's an ongoing process. Tooling integration. You might need to integrate third-party observability tools, e.g., Datadog, Splunk, Prometheus, if your cloud provider's native offerings don't meet all your requirements. Conclusion. The observability pattern is paramount for success in the serverless world. Building applications to be transparent from the outset by strategically emitting structured logs, meaningful metrics, and correlated traces transforms the black box into a well-lit, understandable system. It enables efficient debugging, proactive problem-solving, and informed decision-making, allowing development teams to confidently operate complex, distributed serverless applications at scale. Without a strong commitment to observability, the benefits of serverless can quickly be overshadowed by the challenges of operating an opaque, distributed system. Chapter 10: Serverless Security Patterns. Protecting your applications. In the highly dynamic and distributed landscape of serverless computing, security takes on a new dimension. The shared responsibility model, where the cloud provider secures the underlying infrastructure and you secure your applications and configurations, becomes critically important. While serverless inherently benefits from some built-in security features, like the provider handling OS patching and network infrastructure, it also introduces unique challenges and requires a deliberate security-first approach. The serverless security patterns are a collection of best practices and architectural approaches designed to protect your serverless applications from common threats, manage access effectively, and ensure data integrity and confidentiality. They move beyond basic function permissions to a holistic view of the entire serverless ecosystem. The problem: a shifting security perimeter. Traditional applications often had a clear, defined network perimeter, firewalls, VPNs. In serverless, this perimeter dissolves. Your application now consists of many independent functions, APIs, databases, and event sources, all talking to each other and potentially the outside world. This distributed nature, combined with rapid deployments and ephemeral components, creates new security considerations. Granular access control. Who can invoke a function? What can that function access? The more fine-grained your services, the more granular your access control needs to be. Data in transit and at rest, ensuring data is encrypted everywhere, often across multiple managed services. Input validation. Functions are exposed to various event sources. How do you protect against malicious input? Secrets management. How do you securely provide credentials, database passwords, API keys to your ephemeral functions without hard-coding them? Supply chain security. What code are you deploying and where does it come from? Misconfigurations. Easy-to-make configuration errors can open up significant vulnerabilities. Denial of service, DoS. How do you protect your API endpoints from abuse or excessive traffic? Without specific security patterns, serverless applications can become vulnerable, exposing sensitive data, enabling unauthorized access, or incurring unexpected costs due to malicious use. Identity and access management, IAM patterns, the foundation. The core of serverless security revolves around robust identity and access management, IAM. This is where you define who or what can do what, where, and when. A. Principle of least privilege. This is the single most important security pattern. Every serverless function, every managed service, and every user should be granted only the permissions absolutely necessary to perform its intended task, and no more. How it works: create distinct IAM roles for each serverless function. For instance, a Lambda function processing new orders should only have permissions to read from the order placement queue, write to the order database, publish to the payment processing service, write logs to the logging service. It should not have permissions to delete data from critical tables, access unrelated services, or query sensitive user information it doesn't need for its specific job. Verbal example: imagine a system that handles customer support queries. One serverless function's job is simply to take incoming support requests and save them to a database. It's crucial that this function's cloud permissions only allow it to create new entries in that specific database table. It should have absolutely no permission to delete existing records, modify old ones, or even read from other sensitive tables like user authentication details. This way, if that function were somehow compromised, the damage it could inflict on your broader system would be highly contained. Be separating admin, developer, and application roles. Beyond function roles, carefully manage human access. How it works: use distinct IAM policies for different personas, e.g., administrator, developer, auditor. Developers might have broader access in development environments, but tightly restricted access in production. Application access, what your running functions do, should be separate from human access. Benefit: reduces the risk of insider threats or accidental misconfigurations by human users. Data protection patterns. Securing data both when it's being used by your application in transit and when it's stored at rest, is non-negotiable. A. Encryption in transit, TLS SSL. All communication between your end users, API gateways, functions, and other cloud services should be encrypted. How it works. Managed services, like API gateway, load balancers, S3, DynamoDB typically support or enforce TLS SSL by default. Ensure your custom code connecting to external APIs also uses secure communication. Benefit. Prevents eavesdropping and tampering with data as it moves across networks. B. Encryption at rest. Encrypting your data while it's stored in databases, object storage, and other persistent services. How it works. Most serverless databases, DynamoDB, Aurora Serverless, and storage services, S3, offer built-in encryption at rest, often integrated with key management services, KMS. Enable this for all sensitive data stores. Benefit. Protects data even if the underlying storage media is compromised. III. API and gateway security patterns. The API gateway is often the public front door to your serverless application. Securing it is paramount. API authentication and authorization. Control who can access your API and what they are allowed to do. How it works. Lambda authorizers, custom authorizers. A serverless function that intercepts incoming API requests, performs custom logic, e.g., validating JWT tokens, checking a user database, and returns an IAM policy. Cognito user pools, identity pools. Managed authentication and authorization services for user registration, login, and token management, often integrating directly with API gateways. IAM authorization. Use IAM roles and policies to control access to API gateway endpoints, suitable for internal services or trusted clients. OpenID Connect OAuth 2. Standard protocols for authentication and authorization. Benefit. Ensures that only authenticated and authorized users can interact with your API endpoints. B. Input validation and sanitization. Protect your functions from malicious injections or malformed data. How it works. Perform strict validation of all input at the earliest possible point, e.g., at the API gateway level or at the beginning of your function code. Use libraries to sanitize inputs to prevent direct execution of code or queries. Benefit. Prevents common web vulnerabilities like SQL injection, cross-site scripting XSS, and command injection. C. DDoS protection and throttling. Mitigate attacks that aim to overload your API. How it works. Leverage managed services like web application firewalls, WAF, to filter malicious traffic, and configure API gateway throttling limits to prevent abuse. Benefit. Maintains availability and protects against excessive billing due to denial of service attempts. IV. Secrets management patterns. Sensitive credentials, e.g., database passwords, API keys for third-party services, should never be hard-coded into your functions or stored directly in environment variables. A. Dedicated secrets management services. Use a dedicated, secure service for storing and retrieving secrets. How it works. Services like AWS Secrets Manager or Azure Key Vault allow you to store secrets encrypted. Your serverless functions can then retrieve these secrets at runtime via an authorized API call using their IAM role. Secrets can be rotated automatically. Benefit. Eliminates hard-coded credentials, improves security by centralizing secret management, and facilitates secret rotation. B. Parameter store for configuration. For non-sensitive configuration parameters that might change frequently but aren't secrets, use a secure key value store. How it works. Services like AWS Systems Manager Parameter Store. Similar to secrets, functions can retrieve parameters at runtime. Benefit. Separates configuration from code, allowing dynamic updates without redeploying functions. V. Operational security patterns. Security is not a one-time setup. It's an ongoing process. A. Automated security scanning and testing. Integrate security into your CI/CD pipeline. How it works. Use static application security testing, SAST, tools to scan your code for vulnerabilities, and dynamic application security testing, DAST, tools to test your running application. Include vulnerability scanning for published container images if used. Benefit: catches vulnerabilities early in the development lifecycle before they reach production. B. Centralized logging and monitoring for security events. Make security events observable. How it works: ensure all access logs, from API gateway, functions, databases, audit trails, and security-related events are routed to a centralized logging system. Monitor these logs for suspicious activities and set up alerts for anomalies. Benefit: detects and responds to security incidents promptly. See regular security audits and compliance checks. Periodically review your security posture. How it works: conduct regular internal or external security audits, penetration testing, and validate compliance with relevant industry standards, e.g., GDPR, HIPAA, PCI DSS. Benefit: proactively identifies weaknesses and ensure continuous adherence to security best practices. Trade-offs and considerations: increased complexity. Implementing robust security patterns adds a layer of complexity to initial development. Performance overhead: security measures, encryption, authorization checks, secret retrieval can introduce minor latency, which usually is acceptable given the benefits. Cost: some security services incur additional costs, e.g., KMS, WAF, Secrets Manager. Learning curve: developers need to understand IAM policies comprehensively and adhere to security best practices. Conclusion: serverless security is not about relying solely on the cloud provider. It's about actively designing and configuring your applications with security primitives in mind. By consistently applying patterns, such as the principle of least privilege for IAM, ensuring comprehensive data encryption, bolstering API security with robust authentication and validation, leveraging dedicated secrets management services, and embedding operational security practices into your development lifecycle, you can build serverless applications that are not only scalable and performant, but also highly secure. Security is a continuous journey, not a destination, and these patterns provide a powerful roadmap for protecting your serverless applications in an ever-evolving threat landscape. Chapter 11: Anti-Patterns and Common Pitfalls. What to avoid. Throughout this book, we've explored powerful serverless design patterns that help build robust, scalable, and cost-effective applications. However, migrating to or designing for serverless isn't without its challenges. Just as there are proven solutions, patterns, there are also common mistakes and suboptimal approaches, often called anti-patterns, that can lead to performance issues, increased costs, operational headaches, and architectural fragility. Understanding these anti-patterns is just as important as knowing the good practices. By recognizing what to avoid, you can proactively steer your serverless designs away from potential pitfalls, saving significant time, money, and frustration down the line. The monolith in a Lambda anti-pattern. Perhaps the most common anti-pattern, especially for teams transitioning from monolithic or traditional microservice architectures. The pitfall: instead of designing small, single-purpose functions, developers might bundle an entire application, or a large part of it, into a single, massive serverless function. This often involves large code bases, multiple functionalities, and complex dependencies. Why it's an anti-pattern: reduced scalability. While the function itself scales, internal components within it don't scale independently, negating a core serverless benefit. Increased cold starts. Larger code packages take longer to download and initialize, increasing cold start latencies. Higher costs. You end up paying for more memory configuration than strictly necessary for smaller tasks within the monolith. Decreased resilience. A bug in one part of the monolithic function can bring down unrelated functionalities within the same function. Difficult to maintain and debug. Large, complex functions are harder to test, debug, and update, resembling the very monoliths you might be trying to escape. The fix: break down functionalities into smaller, focused, and independently deployable serverless functions, adhering to the single responsibility principle. Leverage event-driven communication and orchestration patterns, like Fanout or Saga, to link these smaller functions. Excessive synchronous communication / function chaining. Relying too heavily on direct, sequential calls between serverless functions. The pitfall: Instead of using asynchronous events, functions directly invoke other functions in a long, synchronous chain. Function A calls function B, which calls function C, and so on. Why it's an anti-pattern? Increased latency. The total execution time becomes the sum of all functions in the chain plus network overhead between invocations. Each hop adds latency. Reduced resilience. A failure at any point in the synchronous chain breaks the entire transaction. Tight coupling. Functions become tightly coupled, making it difficult to change or replace one without affecting others. Billing complications. You're paying for the entire duration of the request across all functions, even if one is just waiting for another. The fix: embrace asynchronous, event-driven architectures. Use messaging queues SQS, SNS, event buses, EventBridge, or workflow services, step functions for orchestrating multi-step processes. For example, function A completes its task, publishes an event, and then exits. Function B subscribes to that event and is invoked independently. III. Over-reliance on local file systems / in function state. Treating functions as if they have persistent local storage. The pitfall: storing temporary files, caching data directly in the function's ephemeral file system, or relying on in-memory state across multiple invocations. Why it's an anti-pattern? Statelessness violation. Functions are designed to be stateless and ephemeral. Any data stored locally is lost once the function instance is reaped or if a new instance handles the next request. Scale issues. Data stored locally by one function instance isn't available to other instances, leading to inconsistency. Cold start impact. Larger temporary storage usage can increase package size and cold start times. The fix: externalize all persistent state. Use managed services like object storage, S3, for temporary files, databases, DynamoDB, Aurora Serverless, for session data or persistent caches, or dedicated caching services, Elasticache. IV, not optimizing for cold starts, blindly using large runtimes, ignoring the performance implications of initial function invocations. The pitfall: choosing large, heavy runtimes, like Java or Net, for very simple or infrequently invoked functions without proper optimizations, or bundling unnecessarily large dependency packages. Why it's an anti-pattern? Poor user experience. Cold start latency can be noticeable for user-facing API endpoints, leading to slower response times. Increased cost. Longer initialization times mean you pay more for the function's execution duration. The fix: choose lighter runtimes. For latency-sensitive paths, consider Node.js or Python, which generally have faster cold starts. Minimize package size. Only include necessary dependencies in your deployment package. Optimize code. Reduce initialization logic within your function's global scope. Provisioned concurrency warm-up strategies. For critical paths, leverage platform features like provisioned concurrency, which keeps function instances warm, or a simple warm-up mechanism that periodically pings functions. However, don't over-rely on warm-up scripts for non-critical paths, as this can increase costs. Ignoring observability, black box syndrome. Failing to properly instrument applications for logging, metrics, and tracing. The pitfall: deploying serverless applications without centralized, structured logging, insufficient custom metrics, or proper distributed tracing. Why it's an anti-pattern? Debugging nightmare. Pinpointing issues in a distributed, ephemeral environment becomes exceedingly difficult, leading to long incident resolution times. Performance blindness. Impossible to identify performance bottlenecks or understand resource utilization. Cost overruns. Without clear metrics, optimizing for cost becomes guesswork. The fix: proactively implement the observability pattern, Chapter 9. Embrace structured logging, emit custom metrics for business and technical KPIs, and use distributed tracing tools. These are not optional in serverless, they are essential. VI: over-orchestration / over-engineering simple workflows. Using complex workflow services for trivial tasks. The pitfall: employing services like AWS step functions for workflows that could be handled by simpler messaging patterns or even within a single function. Why it's an anti-pattern? Unnecessary complexity. Introduces more moving parts, increasing cognitive load for development and operations. Increased cost. Orchestration services have their own costs, which might outweigh the benefits for very simple workflows. Debugging overhead. Debugging a multi-step workflow can be more involved than a single function. The fix: use the simplest tool that gets the job done. For simple sequences, asynchronous events or basic queues might suffice. Reserve workflow orchestrators for truly complex, long-running, or human-in-the-loop processes where managing state, retries, and explicit flow is critical, e.g., the saga pattern. VII. Hard-coding configuration and secrets. Embedding sensitive information directly into code or unsecured environment variables. The pitfall: storing database connection strings, API keys, or other sensitive parameters directly in the serverless function code or as plain text environment variables. Why it's an anti-pattern. Security vulnerability. Exposes sensitive data, especially if code repositories are compromised or environment variables are accidentally logged. Deployment complexity. Requires code changes and redeployments for configuration updates. Poor management. Difficult to rotate secrets or manage them across environments. The fix: implement the serverless security patterns, Chapter 10. Use dedicated secrets management services, like AWS Secrets Manager, Azure Key Vault, Google Cloud Secret Manager, for sensitive data and parameter stores, like AWS Systems Manager Parameter Store, for non-sensitive configuration that needs to be externalized. VII. Ignoring the principle of least privilege. Granting overly broad permissions to functions. The pitfall: providing serverless functions with excessive IAM permissions, such as full admin access to an S3 bucket when only read access to a specific folder is needed, or access to all DynamoDB tables when only one is relevant. Why it's an anti-pattern. Security risk. If a function is compromised, an attacker can leverage its overly permissive role to access or manipulate unrelated and sensitive resources. This is one of the most critical security vulnerabilities. Auditability issues. Makes it harder to identify and understand the blast radius of a potential breach. The fix: always adhere to the principle of least privilege, Chapter 10. Grant only the exact permissions, actions on specific resources, necessary for the function to perform its task. Regularly review and refine these permissions. Conclusion: serverless computing offers immense power and flexibility, but it demands a different architectural mindset. The anti-patterns we've discussed highlight common missteps that can undermine the very benefits serverless promises. By actively avoiding the monolith in a lambda, embracing asynchronous communication, diligently externalizing state, prioritizing observability, and rigorously applying security best practices, you can navigate the architectural landscape more effectively. Recognizing these pitfalls isn't just about avoiding problems. It's about building more resilient, performant, and cost-efficient serverless applications that truly transform your business capabilities. Chapter 12. The future of serverless, emerging trends and next steps. We've traversed the landscape of serverless computing, from its foundational principles and core building blocks to a deep dive into powerful design patterns and common pitfalls. It's clear that serverless is more than just a passing fad. It represents a profound shift in how we conceive, build, and operate software. But the journey doesn't end here. The serverless ecosystem is continuously evolving, with exciting developments on the horizon. This chapter will explore some emerging trends and offer guidance on how to stay ahead in this dynamic space. The rise of state and stateful serverless. While statelessness has been a defining characteristic of serverless functions, the industry is increasingly recognizing the need for better support for stateful workflows and long-running processes. Managed stateful orchestration. Services like AWS Step Functions have already demonstrated the power of managed state machines for complex workflows. We can expect these services to become even more sophisticated, offering richer control flows, easier integration with diverse services, and potentially built-in mechanisms for human-in-the-loop interactions. Durable functions, e.g., Azure Durable Functions. This concept explicitly allows serverless functions to maintain state across invocations and provides constructs for long-running, resilient workflows that can survive reboots or failures. Expect to see similar capabilities emerge or mature across other cloud providers, blurring the lines between traditional serverless functions and always-on services. Serverless databases and data services. The continued evolution of auto-scaling, pay-per-use databases, like Aurora Serverless, DynamoDB, and managed data streaming services, like Kinesis, Kafka as a service, is critical. These services make it easier to build truly serverless data layers that scale and perform with minimal operational overhead, enabling more complex event sourcing and CQRS patterns. Eventing everywhere. The pervasiveness of events. The event-driven paradigm, EDA, already central to serverless, will only become more fundamental. Enhanced event buses. Cloud event buses, like Amazon Event Bridge, will continue to expand their integrations with SaaS applications and third-party services, making it simpler to connect disparate systems and build enterprise-grade integrations without custom code. Event mesh architectures. For very large organizations, the concept of an event mesh, a dynamic, universal eventing layer that routes events across cloud environments, on-premises data centers, and even different cloud providers, will gain traction. This will further enable loose coupling and real-time data flow across complex enterprise landscapes. Streaming analytics. The confluence of event-driven architectures and serverless compute will fuel the growth of real-time streaming analytics. Expect easier-to-use, serverless native tools for processing vast amounts of event data on the fly, enabling instant insights and reactive systems. Edge computing and serverless. The push to bring compute closer to the data source, reducing latency and bandwidth costs, perfectly aligns with the serverless model. Serverless at the edge. Functions running directly on CDN edge locations, e.g., AWS Lambda at edge, Cloudflare workers, will become more powerful and commonplace. This enables ultra-low latency responses for web applications, real-time data filtering for IoT devices, and localized data processing. IoT and serverless integration. Expect deeper integrations between IoT platforms and serverless functions, allowing for immediate processing of device data, command dispatch to devices, and machine learning inference directly at the edge or with minimal hops back to regional data centers. Improved developer experience and tooling. The developer experience for serverless, while improving, still has room to grow, particularly around local development and debugging. Enhanced local development and debugging. Tools that accurately simulate cloud environments locally will become more sophisticated, allowing developers to test complex serverless workflows and integrations without constant cloud deployments. Standardization and portability. While true cloud-agnostic serverless is challenging, initiatives around open standards and frameworks, e.g., OpenFaaS, cloud events, will continue to evolve, aiming to provide a degree of portability and reduce vendor lock-in concerns. AI-assisted development. Generative AI tools will increasingly assist in serverless development, potentially automating code generation based on event schemas, suggesting optimal resource configurations, or diagnosing issues from logs. vFunction as a service, FaaS, evolution. The core FaaS component itself will continue to mature. Performance optimizations. Cloud providers will continue to fight cold starts and improve the overall performance and efficiency of their FaaS offerings. New runtimes and custom runtimes. Support for more programming languages and the ability to bring your own custom runtimes will provide greater flexibility. Refined pricing models. While pay-per-use is fundamental, expect more nuanced pricing tiers or options for specific use cases, e.g., very long-running functions, functions with burst requirements. Serverless in the enterprise. Best practices and adoption. Serverless adoption within large enterprises will continue to accelerate, leading to more mature patterns and practices. Governance and compliance. As serverless applications proliferate, enterprises will demand better tools and patterns for enforcing governance, security compliance, and cost control across large serverless estates. Hybrid serverless architectures. Integrating serverless components with existing on-premises systems or traditional cloud-hosted workloads will become a refined art, leading to patterns for seamless data synchronization and API gateway configurations. Specialized serverless solutions. Expect to see the emergence of specific serverless solutions tailored for particular industries or use cases, perhaps financial transaction engines, healthcare data processing, or large-scale media transcoding. Your next steps: embracing continuous learning. The serverless landscape is one of rapid innovation. To remain proficient and capitalize on its benefits, continuous learning is essential. Stay curious and experiment. Follow cloud provider announcements, industry blogs, and open-source projects. Experiment with new services and features as they emerge. Deepen your cloud provider knowledge. While the patterns in this book are platform-agnostic in principle, their effective implementation often requires a deep understanding of your chosen cloud providers' specific services and their nuances. Practice infrastructure as code, ISC. This is non-negotiable for managing serverless deployments. Tools like AWS SAM, Serverless Framework, and Terraform are constantly evolving. Prioritize observability. As repeatedly emphasized, the ability to monitor and troubleshoot distributed serverless systems is paramount. Invest time in mastering observability tools and practices. Engage with the community. Join online forums, attend webinars, participate in local meetups, and contribute to discussions. Learning from peers and experts is invaluable. Focus on business value. Remember that technology serves business goals. Always evaluate new serverless trends and patterns through the lens of delivering greater business value, whether through increased agility, reduced cost, or improved user experience. Conclusion: architecting the future with serverless patterns. Serverless computing has moved beyond novelty to become a mature and indispensable architectural style. It's not merely a cost-saving measure, but a catalyst for fundamental shifts in how we build applications, making them more agile, resilient, and scalable by default. The design patterns we've explored, from the efficiency of the fan-out to the consistency of the saga, the strategic migration of Strangler Fig, the historical insights of event sourcing, the performance gains of CQRS, and the foundational importance of security and observability, provide a powerful toolkit. They offer blueprints for navigating the complexities of distributed systems, transforming theoretical concepts into practical, deployable solutions. The true revolution of serverless lies not just in the no servers to manage, but in the mindset it cultivates. A radical focus on events, an embrace of loose coupling, and a commitment to building responsive, fluid, and evolvable systems. As the landscape continues to evolve, armed with the knowledge of these patterns and a commitment to continuous learning, you are now well-equipped to design for the future, building applications that are not just functional, but truly transformative. You are ready to move beyond functions and architect the next generation of cloud-native applications.